Example 7, under internal force convection, flow of oil in a pipeline through a leak. Let's take a look at the question. Consider the flow of oil at 20 degrees Celsius in a 30 centimeter diameter pipeline at an average velocity of 2 meters per second. So after this, we will see the figure of this flow of oil. Next slide. A 200-meter long section of the horizontal pipeline passes through icy waters of a lake at 0 degrees Celsius. Measurements indicate that the surface temperature of the pipe is very nearly 0 degrees Celsius. Disregarding the thermal resistance of the pipe material, determine A, the temperature of the oil when the pipe leaves the lake. B, the rate of heat transfer from the oil. And we will omit question C from our calculation. Okay. So we just focusing more on question A and B. So here, previously, we know that in the example 6, we have cylinder with a diameter. Okay, we have the inlet and the outlet. If in the question mentioned about thin copper tube or any other materials with this word thin, we can assume that the I is equivalent to the out. Therefore, the T surface can be assumed, T surface out can be assumed equal to T surface inlet. So for our calculation, here there is another word or another statement in the question that mention we can actually omit the conduction process for the tube. Okay, this will occur conduction process. So let's take a look at the statement here. Disregarding the thermal resistance of the pipe material. So this means that the pipe material is thin, or the thickness of that tube can be neglected, and the conduction process will be neglected at that point. So when that statement, when the question state that, therefore you can also assume that T surface out is equivalent T surface in. So this is the figure. What I told you that we have the icy lake at 0 degrees Celsius, and then the question state that surface temperature of the pipe is very nearly to 0 degrees Celsius, which means that Ts out here, Ts out is equivalent to 0 degrees Celsius. But we know that the pipe have thickness. So if we draw a pipe, we know that the pipe has thickness. But in the question already state that disregarding resistance of the pipe materials. So which means that we are neglecting the conduction process, and it's also brings the same things that will be happens as thin copper tubes. So we are neglecting the conduction resistance here, R conduction, which means when the R conduction is neglecting, we can assume that this pipe is actually a thin pipe. R conduction neglect, and we can assume that this pipe is actually thin pipe. When we assume that this is actually a thin pipe, therefore the TSI, this is TSI, we have to, and now the outside is TS out. So the TS out is nearly 0 degrees Celsius. What about the TSI? Then because of the R conduction is neglected, and then we may assume that this is actually a thin tube. Therefore, TSI can be equal to TS out. Okay, that is our conclusion for TSI. So the first question asks us to determine the temperature of the oil when the pipe leaves the lathe. So now here, we do not know what is the value of the T exit. Okay. So how do we want to find the T exit? So we know that the T exit, okay, this is, we have to condition, right? Constant surface heat flux, and then second is constant surface temperature. This question falls under number 2, constant surface temperature. Under constant surface temperature, we know that there is equation for Q dot, which is we can use M dot Cp delta T. Can we use this equation? No. Why? Because delta T is Te minus Ti. We do not have the value for Te. That is why the question asks us to find what is the temperature exit of the oil. So we cannot solve the Q dot by using this equation. Next, we have Q dot equal to H as delta T log mean. Wait a minute. In this question, in this equation, we have delta T log mean. In the delta T log mean, we have to have T exit. Can we solve delta T log mean? Yes. T exit can be calculated by using the equation. Okay, it can be calculated. So now what we have to do is we have to find what is the delta T log mean. Okay. So at this point, it's like when we want to find what is the properties, or we want to evaluate the properties of the oil in the in the tubes, we have to evaluate at bulk temperature, where the temperature of bulk temperature is actually Ti plus T exit divided by 2. So again, in this question, is the same as example 5. We do not know what is the temperature exit. Therefore, we assume the bulk mean temperature for this question. You don't have to worry, because for your level, all of these properties will be given, and you may not need to assume the bulk mean temperature, because that is degree level, from degree level up to master or PhD. Okay, at your level, you are required. Your question already give you all the properties for your question, and then at this point, I will explain how this question do some assumption from the bulk mean temperature up to how do we want to find what either our assumption is correct or not. So now the TB that this question assume is equal to 20 degrees Celsius. Okay, because this is as we can see here, why do I have to as we can see here, Ti plus T exit. Okay, do we need why do I have to assume 20 degrees Celsius? The exit would be maybe higher than T inlet, or maybe lower than T inlet. In this case, T exit will be lower than 20 degrees Celsius. Why? Because as we can see here, T inlet is 20 degrees Celsius. IC lake is at 0 degrees Celsius. From here, we can conclude that the heat will be transferred from oil to lake. So when the heat been transferred to the IC lake, this fluid oil will loss of energy, and that loss of energy is equivalent to Q dot. And when there is loss of energy, temperature exit will be less than temperature in. It cannot be greater than temperature inlet. If TE greater than T inlet, therefore there is an amount of heat being added to the system. But now heat has been lost from the system to the surrounding. Therefore, TE is much more lower than 20. So if we take TE is around 20 or 19, so we can get around 20 degrees Celsius for bulk mean temperature. Therefore, that is why I try my first assumption, bulk temperature at 20 degrees Celsius. Then you have to evaluate all the properties, or you have to find all the properties in the table A13 for the row K, V, C, P and Prandtl number. Okay. Now, under constant surface temperature, we know that when the fluid flows in the cylinder, there is so many regions. For example, if you calculate the Reynolds number and you get turbulent flow, under the turbulent flow, the total length, not all length or not the whole length of the cylinder is turbulent. There is a developing laminar flow, or maybe there is a developing laminar flow, entry length of the laminar flow. But in the sea, constant surface temperature, so we have to take a look at the laminar flow for the entrance region, and then we have to take a look at the turbulent region. The equation is totally different. So under the developing laminar flow, we have so many equations that can be used actually. But normally we can use the entry region laminar. Nusselt number is equivalent to 3.66 plus 0.65 d over L Reynolds number Prandtl over 1 plus 0.04 d over L Reynolds number Prandtl 2 over 3. Normally we will use that equation. Okay, when the difference between the surface and the fluid temperature is large, so you have to minus, or you have to subtract between surface temperature and the fluid temperature. Either you get large or just a few maybe 20 degree or 30 degree, not up to 300 or 400 degrees Celsius. that is too large. When there is a temperature difference, large temperature difference, therefore you need to use the entry region lamina by using this equation. With the condition that the fluid temperature, the delta T is large. Okay, and let's take a look at this. So we have a T inlet at 20 degrees Celsius. Bulk mean temperature is at 20 degrees Celsius for our assumption. It might not exceed 20 degrees Celsius. It might be lower than 20 degrees Celsius. And then we have IC lake is around 0 degrees Celsius. If this question falls under developing laminar flow, then the temperature difference is not large. Therefore, we cannot use this equation. Okay, we might use this equation. So the average Nusselt number for the thermal entrance region of flow between isothermal, this is totally out of question because isothermal parallel plates. If there is two parallel plates and the fluid in the middle, so you want to find what is the Nusselt number for the fluid, you can use this equation. So for the cylinder, we focus on these two form of equation. So now, if this question falls under developing laminar flow, suitable equation is this. Okay. And then what if this question falls under turbulent flow? We calculate the Reynolds number, and then the Reynolds number is around 15,000, for example. So we have to assume that fully turbulent flow. So do we have friction factor? So this is out of our method lah. Okay, we are not using friction factor in order to solve what is the Nusselt number. So let's focus on this. Colburn equation has been improvised by Dieters Boiter. So we can only focus on this equation because this equation is much more precise compared to this Colburn equation. So remember, you must focus on this equation for the fully developed turbulent flow. Okay. Again, when the variations of temperature difference is large, therefore you have to use this equation. In this case, the temperature difference is not large, therefore you cannot use this equation. And you have to use this equation if it falls under turbulent flow in tubes. Wait, what is the importance of we know about the laminar turbulent, development laminar turbulent flow, and then turbulent flow? We have to find what is the heat transfer coefficient, because as I mentioned before, as I told you before, we have CST. This question falls under constant surface temperature, and we will use this Q dot equal to HAS delta T log mean. So we can find what is surface area. We can find what is delta T log mean by using the equation. Now we have to find what is the heat transfer coefficient here, H. That is our main focus because H is remain unknown up till now. Therefore, to find H, we have to go and test for the Reynolds number. Either it is in laminar flow, developing laminar flow entrance region, or it is under turbulent flow. Okay? If it's under developing laminar entrance region, then you have to use proper equation in order to find the Nusselt number. Then you have to equate with Nusselt number. Okay, Nusselt number equal to HD over K. Okay, in order for you to find what is the heat transfer coefficient. Now that is the reason why I explain to you about developing laminar flow in the entrance region and turbulent flow in tubes. Okay, now what we are going to do first is to find Reynolds number. So we have to find what is the Reynolds number, equal to, I will use Vd over kinematic viscosity. So we have velocity is 2 meter per second times with diameter is 0.3 meter divided by 9.4 to 9 times 10 to the power of minus 4 meter square per second. So you will get this 636. Okay, your Reynolds number is 636. Now compare this Reynolds number with Reynolds number if below than 2300, therefore this is laminar. Okay, now your flow Reynolds number is 636, which is below than 2300, therefore this is laminar flow. Okay, so we know that this is laminar flow. So let's take a look at the thermal entry length. Okay, thermal entry length for a laminar flow, you may refer to my previous video. So 0.05, so Reynolds number times with Prandtl number times with D, and equal to 0.05 times with 636 times with 10,863 and times with 0.3. So you will get this 103,600 meter. So that is the length, thermal entry length for this question. And when we compare this thermal entry length with our length, with the length of a cylinder or the tubes in this question, we found that the tubes is much more lower, less than, the length of the tube is less than 103,600 meters, and therefore this length falls under entry region. Thermal entry region is 103,600 meters. So if I can draw here, so for that question, the thermal entry region is length is 100,000 meters. But now this is thermal entry. So you have your length of your cylinder is 200 meters only. So your length, your total length of your cylinder falls under thermal entry region. Therefore, this falls under developing laminar flow. Okay, this one, developing laminar flow in the entrance region. So your laminar flow, you already determined that your flow is laminar. So you have laminar flow, and your cylinder, your tubes, your pipeline falls under entrance region. The total length of your pipeline falls under thermal entry region. Therefore, we have to find the equation in developing laminar flow. Okay. Under the developing laminar flow, we will use the entry region laminar Nusselt number equal to 3.66 plus this equation. So substitute into this equation, find what is Nusselt number. So from there, so you can find that your Nusselt number is equal to 33.7. Okay, that is your Nusselt number. You have to substitute into developing laminar region in entrance region. Okay, so from here we have to equate this equation with h d over k. Therefore, rearrange to find what is h. So your Nusselt number times with k 0.145 watt per meter dot Kelvin and divided by diameter is 0.3 meter. So you will get your H is 16.3 watt per meter square dot Kelvin. Okay, now we have H. So we already solved for the H. Now we calculate AS. Next, we proceed to delta T log mean. So AS is pi dl. So we have pi, diameter is 0.3. We have to times with 200 meter. You will get 188.5 meter square. Okay, that is for your surface area. Now we move to delta T log mean. To find delta T log mean, we have to find what is the T exit. From the equation, T exit is Ts minus Ti exponential minus H As over m dot Cp. So here we have mass flow rate. Now we need to calculate what is the mass flow rate of your question. So mass flow rate is rho AC V. So here for the mass flow rate, we need to calculate cross-sectional area. Since if I draw this figure, sorry, okay, here mass flow rate, fluid flows in this at this area, on this area. Therefore, you have to calculate AC, and here is AS. So heat transfer will occur at AS, mass transfer will flows on AC. So therefore, area in mass flow rate is AC. So you have to calculate AC pi d squared over 4. So substitute. So your rho is 8.1 times with pi 0.3 pi d squared over 4. So close, and then times with velocity is 2 meter per second. So you will get your mass flow rate is 125.6 kilogram per second. So substitute all the values here inside this, and you will get your TE is equal to 19.74 degrees Celsius. Okay, then from here, substitute all the value into delta T log mean. So we have Ti minus Te divided by ln, okay, Ts minus Te divided by Ts minus Ti. So you get this, substitute into this equation, and then you will get that delta T log mean is negative 19.87 degrees Celsius. Now wait, from T exit, okay, previously I assumed the value for the T bar. So T bar is Ti minus Te divided by 2. Now I already get what is the value of Te. Okay, Te is 19.74. So I get 20 for inlet plus 19.74 and divided by 2. So I will get around 19.87. 19.87, which is approximately 20 degrees Celsius. Then I may not need to assume again and redo the calculation and iterate again and get the value for the T exit and or the T bar that is equivalent to assume value equal to assume value. So my assumed value is okay. Okay, the T bar temperature is 20 degrees Celsius and I get 19.87. We get around 20 degrees Celsius. Okay, after that, after you get the TE, you have to plug in into delta T log mean. So this is the equation, and you will get this value is equivalent to 19 minus 19.87. That is delta T log mean. Then you have to substitute into Q. Okay, Q dot equal to HAS delta T log mean. So we want to find what is the rate of heat transfer. So your H is 16.3. Okay, 16.3 times with AS 188.5 times with minus 19.87. So you will get the value for Q dot is minus 6.11 times 10 to the power of 4 watt. So from this value, you do not have to worry about this negative sign. This negative sign represents that the Q has been released to the atmosphere. Okay. If you want to state that how much energy has been released, you just only need to state that it is around 6.11 times 10 to the power of 4 watt. If you want to tell somebody that you get rate of heat transfer is equivalent to minus 6.11 times 10 to the power of 4 watt. This means that negative sign means release. Okay, your energy released to the surrounding. If you get positive value, it means that energy has been added to your system or to the system. Okay, we have already answered question A and B, and thank you.